ଫୋନ୍ ପେ ଦଉଛି।
Good afternoon, everyone. At the outset, I would like to request all participants, please mute yourself and don't press the presentation button so that we can conduct the session without any disturbance. Start करूँगा। सॉफ्टवेयर दिख रहा है, नोटिस है। Hello, am I audible? Hello? Audible? Good afternoon, everyone. With the blessings of Lord Jagannath, let me start today's session. Esteemed Principal, Udala College, Udala, revered Chief Guest cum Chief Speaker of today's webinar, Dr. Vivekananda Nayak sir, respected staff members and students. At the very outset, I would like to express my heartfelt gratitude to all the participants who have joined from different parts of this country and also from abroad for your overwhelming support and cooperation in these days. It's my pleasure and privilege to welcome you all to our 15th webinar. Here I also welcome our Honorable Principal, Sir Professor Gopal Chandra Behra, whose continuous support and cooperation has motivated us to organize a series of webinars in these days. I express my heartfelt thanks to him and also hope that he will continue his support and cooperation in the coming days as well. I also welcome HOD Physics and convener of today's session, Professor Snigdha Agarwal, Madam, and co-convener Gajendra sir. I also welcome Assistant Coordinator IQAC Satyavrata sir. Further, it's a matter of honor and a privilege for me to welcome our Honorable Chief Speaker of today's session, Professor Vivekananda Nayak sir, who is now working as Assistant Professor PG Department of Applied Physics and Ballistics, Fakirmon University, Baleswar, Odisha. Sir, I on behalf of all the staff members and principal in the Department of Physics and IQAC, I extend my sincere gratitude and respect and welcome you to this August gathering. Hope our sirs' deliberation on the chosen topic will be highly informative one and a useful one, not only for the department, our faculties as well as students, but also all the participants who have joined from different parts of this country and abroad. Once again I thank all the participants and sincerely welcome you all to our today's program. Now, as per our agenda, I would like to invite our Honorable Principal Professor Gopal Chandra Behra sir to keep his presidential address. Principal sir, please.
Thank you, Dr. Panda sir, for your sweet speech. Good afternoon to one and all. Esteemed Chief Guest, Chief Speaker of today's webinar, Dr. Vivekananda Nayak sir, Assistant Professor, PG Department of Applied Physics and Ballistics, Fakirmon University, Baleswar, Odisha. Respected participants who have joined from different parts of the country and abroad, my dear colleagues and students. At the very outset, I welcome you all and thank you for joining in our 15th webinar. I thank Professor Snigdha Agrawal, Madam, HOD Physics and convener of today's session, and also Professor Gajendra sir, and convey my good wishes to her department and her team for organizing such an educational program in the campus. In this respect, I also extend my thanks to the IQAC officers in charge, Dr. Prafulla Kumar Panda sir and Satyavrata Malik sir, for taking all possible initiatives to organize such a webinar in our college, with an aim to inspire our students as well as teachers and updating their knowledge. It's my pride and privilege to speak a few words about my college. Udala College, Udala was established in the year 1965. Since then, it has walked miles, though it has to cover more in the years to come. Our college is the one and only Novel Center in the sub-division, being one of the premier colleges in the district and in Odisha as well. We have 14 numbers of honor subjects. Our students have made us proud by securing top position at the university level every year. Our college has been accredited with B++ by the NAC in the year 2016. The topic chosen for today's webinar, Fundamental Constituent of Matter, is a very important and useful theory. It has undergone two revolutionary changes from atoms to proton and neutron, and then on to quarks and leptons. All these quarks and leptons have been seen by now along with carriers of their interactions, the gauge bosons. But this story is not completed. A consistent theory of mass requires the presence of Higgs bosons along with SU, SY particles which are yet to be seen. I welcome our Honorable First Person and Chief Speaker of today's session, Dr. Vivekananda Nayak sir, to keep his deliberation elaborately on the topic. Lastly, I once again congratulate the HOD Physics and her team and the IQAC for organizing such a useful session on the very topic. I wish a great success to this program. Thank you all.
Thank you, sir. Thank you for your kind words and inspiring, motivational words. Now, I would like to request Professor Snigdha Agarwal, HOD Physics, for a brief introduction on the topic. Please, madam. Please.
Hello. A very good afternoon to everyone. Firstly, I would like to thank Professor Kanda sir and the principal sir to join this meeting and help us to organize this type of webinar. So, esteemed principal sir, Professor Gopal Chandra Behra, respected Chief Speaker Vivekananda Nayak, Assistant Professor FM University Balesar, respected IQC Coordinator sir, Panda sir, and Satyavrata Malik sir. So first and my respected participants and my dear colleagues and students. I am immensely pleased to thank everyone for joining today's webinar on the topic fundamental constituents of the matter. So before that, I just want to give a short introduction about the topic. So physicists have identified building blocks that are the fundamental constituents of the matter. Our everyday life is just made up of three of these building blocks. As we know it, there are quarks, down quarks, and the electrons. All these particles are needed to make protons and neutrons, and further atoms and molecules.
Continue.
So in 1960s, Francois Englert and Peter Higgs were among the several physicists who proposed the mechanism to explain why the most building blocks of the universe are mass. The mechanism predicts particles, the Higgs boson, for which the Francois Englert and Peter Higgs were awarded the Nobel Prize in the year 2013. So, the further elaboration of this topic, the fundamental constituents of matter, will be given by our chief speaker, from Honorable Resource Person, Dr. Vivekananda Nayak. So, thanking you all.
Thank you, madam, for your brief topic introduction. Now, it's time to listen to our Honorable Chief Speaker of today's session. So before that, let me introduce him. It's my honor and privilege to welcome and introduce our Honorable Chief Guest, come Chief Speaker of this session to this August gathering. Our Chief Speaker, Dr. Vivekananda Nayak, sir, is a man of excellence, a good teacher, an excellent academician, and a genuine lover of physics. Dr. Nayak qualified NET twice in June and December 2006 and GATE in the same year too. At present, Dr. Nayak is working as an assistant professor of physics, PG Department of Applied Physics and Ballistics, Fakir Mohan University, Balesar, Odisha. During his professional career in the university, Professor Nayak has successfully performed his duties and responsibilities as a teacher and academic researcher. His area of research has been gravitation and cosmology, particle astrophysics. As an academic researcher, Professor Nayak has published 18 numbers of articles in different national and international journals. He has also presented many papers in different seminars and conferences organized by different universities. Professor Nayak has been conferred with some prestigious awards for his research works and for his excellent contribution to physics, such as Young Scientist Award in Physical Sciences for the year 2015 by Odisha Vigyan Academy. Secondly, Young Scientist Award, another award he has also achieved, that is a Young Scientist Award in Theoretical Physics for the year 2016 by Odisha Physical Society. Professor Naik is indeed one of the most humble, intelligent and enthusiastic personalities and a great motivator for his students and colleagues. Sir, really all the staff members of Udala College are immensely honored to get you as the chief speaker for today's webinar on a very reliable and pertinent topic, fundamental constituents of matter. Sir, once again, I on behalf of the principal Udala College and HOD Physics and the IPSC, I extend a warm welcome to this session and extend this hand over this session to you, sir. Please, sir. Vivekananda, sir, please. Continue, sir.
Thank you, sir, for this nice introduction. Am I audible, sir?
Yes, sir. Yes, sir. Continue. Fine.
Good afternoon, all. I am really thankful to Udala College, particularly Principal Gopal sir, Ponda sir, and Snigdha madam and Gajendra sir for inviting me and giving this opportunity to interact with you.
Sir, your video is off, sir. Just, you can
Oh,
on. Sir. Keep on, sir.
okay, sir. Not sharing. Okay, sir. Hello, sir. Hello.
Yes, sir. Yes, sir.
Sir, is my slide visible?
No, sir.
Okay, there's a problem in internet, I think. Am I visible? Hello?
No, sir. Let me see. I think if it is pinned, then it can show. Let me check yours.
Why is it not working?
No, sir. It has not been opened, sir, till yet.
Oh, sir, give me some time. I will use
Okay.
another.
Okay.
Sorry for the.
Okay, sir.
Oh, it denied permission. Oh, sir, give 5 minutes. I will
No.
take another system.
Okay, sir. Okay. No problem. ଟିକେ ମଝିରେ ବ୍ରେକ୍ ଟିକେ ଲକଡାଉନ୍ ହେଇଗଲା ବ୍ରେକ୍ ଲକଡାଉନ୍ ଟିକେ ରହୁଛି କ'ଣ 5-10 ମିନିଟ୍ ବଦଳିଲା ଜିଓ
Sir, am I audible?
Yes, sir. Loud and clear, sir.
Okay, sir. Sorry for this inconvenience. I actually okay. The topic of my today's presentation is fundamental constituents of matter. So, as we know, when people start from thinking about this universe, they are able to sustain after fulfilling their basic needs, then the first thing they want to know how this world made of. Okay, this is the question comes with us from the very beginning of the human civilization, and people try to solve this, and with time they try to answer it. So comes to we Indian people actually believe that our world is made from 5 constituents, which is known as Panchabhuta. So now it is visible, sir?
Yes, sir. Yes, sir. Yes, sir.
Now it visible, okay, sir. Thank you, sir. Okay. Sorry for this. Okay. So the topic of my title is Fundamental Constituents of Matter. In this topic, I want to actually answer two questions. First one is what are the elementary constituents of matter, and the second one is what are the forces that control their behavior at the most basic level. Also, I discuss most of the properties of the elementary constituents. Now, as I already told, the question, what is the world made up of? This question comes with the human beings from the very early days of human civilization, and people try to answer it, different civilization. For example, we, Indus Valley civilization people believe that our world is made from five constituents: Vayu, Agni, Jal, Prithvi, and Akash. But Greek people, they believe
Sir,
world is made from four.
sorry to interrupt,
Hello?
sir. Sorry to interrupt, sir. Sir, your screen is not visible, sir.
It is not visible.
No, sir. Again, try.
Okay, sir. Now, sir, visible?
Yes. Yes, sir.
Sorry, sir, for this inconvenience. Actually, I am using a laptop of my friend. Oh, okay. So, we people believe that our world is made from five elements, but Greek people believe world is made from four constituents, that is air, fire, water, and earth. And this belief goes up to 18th century, but then people try to actually learn it scientifically, and they found that if you break a matter, we found a molecule, and molecule contains all properties of matter. You can say the smallest unit of matter. Then people try to break it and finally found atoms. The molecules are made from atoms. In 19th century up to 19th century, it is a belief that the matter made from atoms and we cannot break atom. But in the year 1897, J.J. Thomson first discovered electron, and he can say that electrons are found inside atom, and other discovered nucleus. So inside atom, there is centrally a positive charge nucleus, and electrons are revolving around it. But then people try to break the nucleus, and fortunately they found it contains one positive charge proton and another neutron. That proton provides the electrostatic force to electron, due to which electron is revolving around the nucleus, and same number of proton an atom contains as electron. Then in 20th century, people try to go more smaller scale, and they found protons and neutrons as breakable, and they contains quartz. So today our picture is quartz and electron, which is comes under a group of particles known as lepton. Lepton means lightweight. So quarks and leptons, they are the fundamental constituents of matter. So today our belief is that may in future someone see some smaller object inside the quark or electron. So if you come to size, the size of a virus, let's say coronavirus, is order of 10 to the minus 7 meter, but molecule size is 10 to the minus 9 meter. If you break them to atom, whose size is 10 to the minus 10 meter, and nuclear size is 10 to the minus 14 meter. If you break the nucleus, you get proton, neutron, whose size is nearly 10 to the minus 16 meter, and quark size is nearly 10 to the minus 18 meter. So this is the present structure of elementary particle or element constituents of matter. You see, if you break matter, you get molecules, and inside molecule you found atoms, where centrally.
Sir, it's not running, sir. It's static, sir. From the first page, only the first page is visible, sir.
Not other pages.
No, sir. It has not been run, sir.
Sir, sir, let's do run करनी slide टा देखूँगी तो
Slide is visible, sir. But you have to change the slides.
slide is not changing. I'm changing the slide.
No, sir. Slide is not changing. Only the first
Okay,
page is
sir.
visible.
Next. Okay, sir. Due to poor connection, I think, sir. Sir, put it there. এটা করতে Now, am I audible?
Yes, sir. Audible, sir.
Showing. Permission and to screen share. What is reading? Comment. Sir, where am I? Waiting permission to share. Oh. And now it is visible? Sir?
Sir. Yes, sir. Yes, sir. Yes, sir.
Now visible?
Yes, yes.
Okay. हाँ सर अली Yes, sir. Hello.
Yes, yes, sir.
Okay, sir. So matter is made from molecules, and if you break molecules, you get atoms where central positive nucleus and electrons are revolving around it. When you break nucleus, protons and neurons are made from quarks. Now, the physics which deals with this elementary particles are known as particle physics. As you know, so elementary particles are basic constituents of matter. So to break matter into small pieces, we need high energy. For example, if you break atom to get an electron, you have to provide some energy of a range electron volt. For hydrogen atom, it is 13.6 electron volt. If you break a nucleus to get a proton, you have to provide MeV, mega electron volt energy. Mega electron volt means 10.6 electron volt. So similarly, if you want to break proton, you know much higher energy, maybe order of GeV, giga electron volt, 10.9 electron volt, and then more. So also for observing small particles, we need high energy because for a microscope, its resolution depends on wavelength by sin theta, and wavelength is inversely proportional to momentum. Or if wavelength or which gives size is very small, then momentum obviously is very large. So high energy is needed to observe small particles. For that reason, this branch of physics is also known as high energy physics. So present energy achieved at LS Large Hadron Collider with the particle physics lab, where we got the maximum energy 14 tera electron volt. Tera electron volt means 10.12 electron volt. But in theory, we may discuss much higher energy, which is actually Planck scale energy 10 to the power 19 GeV, 10.19 giga electron volt energy. And slightly higher energy is the time where the universe was created. Yes, elementary particles have two important properties which were not observed in classical object case. One thing is it has intrinsic angular momentum, that is spin, and another property is it has parity. Classically, this parity is known as spatial inversion. It inverts the space coordinate. Now go to the spin. What do you mean by spin? Spin is associated with orientation of a particle about its own axis. So orientation about own axis is characterized by spin. And if a particle can orient about its axis in 2s plus 1 ways, then it has spin s. If plus 1 way, then a spin s. If you put s is equal to 0, that means we get 1 way. So whatever macroscopic object we see, if they orient about one axis like that, they orient in one way. But in microscopic level, elementary particles, they can orient in more than one way. So they have an extra property which is known as spin. If they can orient in 2s plus 1 way, the spin is s. Electron can orient in 2 ways, so their spin will have 2 into half plus 1 is equal to 2. And like angular momentum, spin is a vector. Since it is angular momentum, it is a vector. So it is obeys the rules of vector addition. If you add two vectors, then suppose a plus b, then its magnitude will be square root of a square plus b square plus 2ab cos theta. And you know cos theta varies from -1 to +1. So between a plus b to a minus b, it can take any value. But when we consider it to quantum mechanics, because the elementary particle size is very small, so our classical laws fails to explain them, we use quantum mechanics. And if in quantum mechanics we know that everything is quantized, but you know from Bohr's theory, angular momentum is quantized. L is equal to ns plus or ns by 2 pi, that n varies from 1 to 3. So difference between two consecutive angular momentum must be 1 according to quantum mechanics. So when you add two spin or angular vectors in quantum mechanics, suppose it is a vector 2 with R3, then actual to vector addition, it can take any value between 2 plus 3, 5 to 2 minus 3 mod 1, 1 to 5. But in quantum mechanics addition, we only take the value 1, 2, 3, 4, 5. Because the difference between yes, sir.
Excuse me, sir. Actually, the slides are not running. It is stick to only one slide, first slide or second slide. I don't know, but actually the PPT is not running.
Not running. Okay. Okay.
No, only for the only the first slide or second slide is displayed. That is the problem.
Yes,
Okay.
yes, yes.
Now it is running.
Yes, sir.
Yes, sir.
Seconds. Then
Yes,
yes, sir.
Running.
yes, sir. Yes,
Yeah,
sir.
yeah, yes, sir. Okay.
Okay, sir.
Thank
So
you.
I am not released full screen. Okay, in this way, there may be problem in the laptop. So
Okay, fine.
okay, thanks. So again, according to spin, there are two kinds of particles. One of spin half particles, they are called fermions, and another of spin integral spin particle, they call bosons. Fermion spin half means the spin either half, 3 by 2, 5 by 2, etc. The example are electron, proton, neutron, they are fermions, and all electron, proton, neutron have spin half. They obey one type of statistics, Fermi-Dirac statistics. But main important point is all fermions obey Pauli's exclusion principle. You know in your plus 2 Pauli's exclusion principle means no two electron can stay in one state, or all four quantum numbers of two electrons are not same. But this is not, this is true for all fermions, not only electron, it is true for proton, it is true for neutron and other fermions. So Pauli's exclusion principle, you can say no two identical fermions have all four quantum numbers alike. So main thing is all fermions obey Pauli's exclusion principle. So you cannot put two identical fermions in one state like electron or proton. So you put two electrons when one of spin third component of spin plus half, another of third component of spin minus half. So it is 1s2. Similarly, you have got the cell structure. You go to next p cell, p subcell, then d subcell, because you can two electrons subcell. At most you can take if their third component of spin is opposite. You to get the cell structure. Similarly for proton and neutron, you got the cell model in nuclear physics, because like electron they have also cell structure. Proton neutrons are also fermions. No two fermions, protons or neutrons can stay in one state. So at most you can put two protons having spin third component of spin opposite. So you got like electron, they have also structure, cell structure. But bosons, integral particles are known as bosons. For example, photon is a boson, and Higgs boson is a God particle who gives all particle mass. That is a boson. Boson means Higgs particle spin is 0, photon spin is 1. They are both bosons or both particles. They obey both Einstein statistics. And these bosons don't obey Pauli's exclusion principle. Any number of bosons can stay in one state. So if you assume electron is a boson, then 100 boson can stay in a state. So there is no affinity to stability, no molecule formation. If electron, proton or neutron are bosons, then you cannot find any molecule or anything involved. So if we are fortunate that electron, proton, neutrons are fermions and obey Pauli's exclusion principle, no two. Next is parity. Second property of fundamental particles is parity. Parity in classical it is known as spatial inversion. Spatial means space coordinate. It interchanges the space coordinate, and we can achieve it by 180-degree rotation about an axis followed by reflection of that axis. Classically you can obtain, if you rotate, suppose we have three axis x, y, z, you rotate this system 180-degree about y-axis, so obviously z and x change their position, z goes to z prime and x prime 180 rotation, and if you reflect y-axis then y goes to y prime. So this is the parity operation or spatial inversion operation, and due to this you see x goes to minus x, y goes to minus y, and z goes to minus z. So for that reason the spatial space coordinate inverses. So due to parity operation, space coordinate inverses. So you can write it on parity P operator. So in eigenvalue equation you write P psi xyz is either n xyz. Then if you operate again, then this minus x goes to x, minus y goes to y, and minus z goes to z. So P square eigenvalue will be 1. So P eigenvalue will be plus 1 or minus 1. So if you operate P, either you find plus 1 or minus 1. If you got plus 1 eigenvalue, then it is called positive parity or even parity. If you got minus 1 eigenvalue, then you got odd parity. And all physics laws are invariant with respect to parity transformation. Whatever laws, equations we study in physics, all are invariant under parity transformation. So, for example, for position vector R, or you can say if you operate parity is a vector, is a x, y, z coordinate change minus x, minus y, minus z, so it becomes minus R. It is x, y, z, if you take common minus, then minus of R. Similarly, for a momentum vector, if you change its coordinate so under parity, you find minus x, minus px, minus py, minus pz, that is equal to minus p. And if you take the angular momentum, which is the cross product of r plus p, then r goes to minus r, p goes to minus p. Minus minus plus, you found r cross p. So here all are not behave on parity and those vectors we are on vector. So we have in plus 2 we know there are two types of physical quantities, scalar and vector. In scalar have magnitude and vector direction, but in but no way you can define it. The scalars are the physical quantity which remains invariant under rotation, and vectors are the physical quantity which varies under rotation. But again, scalars can be divided into two groups. Scalar like your whatever mass, energy, all that type of scalar, actually they remain invariant under parity operation, or for them parity is positive. But another kind of scalar, for them parity becomes negative. For example, magnetic flux density. So we call them pseudo scalar. Similarly, for vector, we call the vector which have negative parity like r, p, all are vector, but angular momentum is a pseudo vector whose parity is positive. So in our particle physics or theory of elementary physics, we consider all particles in terms of spin. So spin zero particles as known as scalar. It has no third component, only one zero. A spin one particle has three third components, plus 1, 0, minus 1, like your vector three component. So spin one particles are treated as vector. So scalar means, so you can say scalar can be written as 0 plus in terms of spin and parity. A pseudo scalar 0 minus, vector 1 minus, axial vector 1 plus. 1 0 refer for spin and the superscript plus minus refer to its parity. Then come to basic interaction in nature. There are four fundamental interactions in nature. One is gravitational interaction originated to mass, another is electromagnetic interaction originated to charge, and other two are found in nuclear level, strong force, strong interaction and weak interaction. Other type of force, mechanical force, friction, that has electromagnetic origin. They come from the electromagnetic field. If you see in microscopy level, they originate from electromagnetic interaction. What we see in our day-to-day life experience, these two types of interactions, gravitational interaction and electromagnetic interaction. These two are long range forces. They have infinite range. You imagine Earth is revolving around the sun due to this gravitational force or gravitational interaction, when the distance between Earth and sun is 15 crore kilometers. So it is a long range force. It acts whatever be the distance between two objects. Similarly, electromagnetic interaction acts between two charged particles, whatever may be the its distance. Now these are the property of these four forces. These are four fundamental forces. Gravitational force, as we discussed, its range is infinite. Electromagnetic range is infinite. A strong and weak force are found inside the nucleus. Nuclear size is femtometer. So strong force is 10 to minus 14 to 15 meters. So strong force is found whose range is 10 to minus 15 meter, and weak force has range 10 to minus 18 meter. And in compared to strength, strong force has strength 1, so electromagnetic have strength 10 to minus 2. If you assume strong strength 1, then electromagnetic is at 10 to the minus 2, weak force at 10 to the minus 7, and gravitational at 10 to the minus 39. So gravitational force is the weakest force of nature. And in terms of lifetime, how quick they interact, this interaction of the time period for which the interaction occurs. Actually, from lifetime we know whether the interaction is strong, weak, or electromagnetic. For strong interaction, lifetime is 10 to the minus 23 seconds. It occurs within 10 to the minus 23 seconds. For electromagnetic, 10 to the minus 20 seconds, and for weak interaction, the lifetime will be 10 to the minus 8 to 10 to the minus 10 seconds. And since these interactions, all interactions are mediated by some particle. And so the strong interaction is mediated by particles called gluon, which we discuss in the next slide. And the electromagnetic interaction is mediated by photon. You know that light is quanta of photon, so electromagnetic radiation is mediated by photon. Gravitational interaction is mediated by one kind of particle graviton, which was associated with gravitational wave, which was discovered in 2016. Then weak interaction is mediated by particles called W plus minus W and Z0. W for weak and Z0 another particle, chargeless particle. They are actually massive, while the other three mediating particles have mass is equal to 0. They are massless particles. Gluon, photon, and gravitational and massless particles. And they have also spin. Gluon has spin 1, photon has spin 1, and W plus 1 is spin 1, and graviton has spin 2. So spin 1 means vector. So electromagnetic theory we study in terms of vector mu, because photon is a vector. When go to gravitation to study the gravitation, you know that branch is known as cosmology, where we use tensor, because it has graviton has spin 2. Spin 2 quantity are denoted by tensor. How you know interaction is weak or electromagnetic or strong? No, weak interaction means a neutrino must present there. It's a signature of one kind of lepton, signature of weak interaction. And if photon present, it is electromagnetic interaction. And hadrons, we will discuss in the next slide, one kind of particles made from quark. Hadrons means particles made from quark. If they present, then the interaction is called strong interaction. Now go to first kind of particles, neutrino, they comes under lepton. Not only neutrino or electron also come on this two lepton. As we discussed, electron has spin half, leptons have spin half, so they call fermions. And leptons don't participate in strong interaction. Leptons are only participate through weak and electromagnetic. It is charged lepton means electron, muon, which are charged non-zero charge, they participate through electromagnetic interaction. Otherwise, neutral leptons are the signature of weak interaction. Neutral leptons are neutrinos. Neutrinos are the signature of weak interaction. They participate only in weak interaction. And in all our interactions, all these lepton numbers are conserved quantity. All lepton means lepton numbers are also divided into three categories. One is electronic lepton, muonic lepton, and tauonic lepton. So electronic lepton, electron has lepton number 1, and neutrino correspond to electron has electron lepton number 1. Similarly, for all particle muon and its neutrino tauon, and then neutrino has muonic and tauonic lepton number. And individually, each one is conserved in interaction. So then, when you come to beta decay, you know neutron goes to proton, electron, and plus a neutron, anti-neutrino, anti-particle of neutrino. Actually, this is a electron type neutrino. You cannot write it muonic or tauonic because electron is present. Electron has electronic lepton number 1, so there must be a electronic neutrino whose lepton number will be -1. For that reason, it is anti-neutrino, anti-particle of electronic neutrino. If it is only particle, it has also lepton number 1, so it will not be conserved. Okay. Then comes to another particle, quark, because quarks and leptons are fundamental particles. They got quarks. Quarks are also spin half elementary particles, and they used to create hadrons. And what is it? The quarks are found in 6 flavors: up, down, charm, strange, top, and bottom. These are 6 kind of quarks. And quarks has the important property, they have color. They exist in 3 colors: red, blue, green.
three quarks have three colors, but quarks are combined in such a way that all naturally occurring particles are colorless. So quark of red, blue, green, but they combine in such a way that we got a colorless subject. Since these are three basic colors, if you add all three in same amount, then you get colorless. Or if you add red with anti-red, or blue with anti-blue, green with anti-green, then we also get colorless object. So colorless means each color is present in same amount or net color is zero. So what type of combination are possible? Since red, blue, three types of colors. So if you add all three, like your sunlight contains seven colors. If seven colors present in the same amount, then you got white. Similarly, if three quarks present in the same amount, three colors present in the same amount, you got the colorless object. For that reason, quarks. Another combination is red, anti-red, blue, anti-blue, green, anti-green. So one quark and one anti-quark. Anti-red means anti-quark. So only two combinations are generally possible for formation of particles from quark. One is three quark combination, another is one quark, one anti-quark combination. And this three quark combination is known as baryons, and one quark anti-quark combination is known as mesons. So we can also from the properties of quark, you can find the properties of these baryons and mesons. Since quark have spin half fermion, so if you add three halves, you found either is a vector. So half plus half is equal to 0, 1. If you add another half, it will be half or 3 by 2. So either they have spin baryon of spin half or 3 by 2. Similarly for mesons, the quark have spin half. And another quark of anti-quark, spin is positive, spin always have, but third component may be opposite to plus minus. So half you have, it will get 0 and 1. So mesons have 0 and mesons have spin 0 or 1. 0 on scalar meson and 1 on vector meson. I don't know. And half particles are known actually spinors. Spin half particles called spinors. So if you are three quarks, you got baryons. So they have actually half integral. If you are three halves, you got either half or 3 by 2. They are half integral particles and they interact through strong, weak and electromagnetic interaction. These are the baryon particles. Or proton, neutron, they are baryons. As we discussed, proton contains 3 quarks, neutron contains 3 quarks, and similarly sigma, cascade, lambda, omega, delta, these are baryon particles. And another type of particles which is called major, for spin either 0 or 1, they, if you add quark and anti-quark, you found this pion, tau, rho particle, eta and W particle. Then come to quark. What are the actual properties of quark? Generally among 6 types of quarks, the up, down, tungsten, top, bottom, all light quarks, UDS are known as light quarks, and most of the hardens are made from these light quarks, UD and AS quarks. So the particle which contain AS quark is known as strange particle. AS quark has a special character which is a strangeness number. So this type of particle which contain AS quark are called strange particles. Particle are named so strange particle because they form in pair through strong interaction but decay individually through weak interaction. Why they call strange particle? They formed in pair through strong interaction but decay individually through weak interaction. The strong particle, strange particle decay is a weak interaction, though they form in strong interaction. Due to this property, they call strange particle, and the particles which contain S quark are strange particles. So how interaction between quarks occurs? Actually, like other force, the quark-quark interaction is mediated through a particle known as gluon. Glue means gluon. Glue joins two things. So gluon particle which joins to quark, anti-quark or three quark. And actually this gluon, since quark has a color, this gluon is a bicolor object. It has two colors, one color and one anti-color. From this combination you can find 8 types of gluon exist. So what are the other properties of quark? No free quark is found in nature. You cannot see free quark. We found inside it proton and neutron, but you cannot find a free quark because there are some reasons. First reason is quarks are confined inside the hadron. You cannot take quark from outside the hadron because the force or potential between them which bind them, that potential is like this V cubes. Quark potential is minus A by R plus B R. This type of potential exists. When R is small, A by R term is dominant. When R is large, B R term is dominant. So A by R negative sign means when R is small, they repel each other. When R is large, they attract each other. This is the property of quarks. When they are very closer, they repel each other, but when they are separated by distance, they attract each other. For that reason, you cannot extract a quark from proton. A strong force exists if they come up to that size, you call periphery of proton, then another quark drag it. So it cannot go outside this. So it is the nature of strong potential force. For nuclear force is a strong force. For that reason, we saw nuclear force is an attractive force having repulsive core. Nuclear force is an attractive force. It attracts externally, having a repulsive core. But when distance between two nucleons is very small, they repel each other. Due to that, all nucleons are not combined. Since it is attracting, they may follow another nucleon. One nucleon may follow over another nucleon, but that does not occur due to this repulsive nature. A nuclear force are attractive, having repulsive force. Another thing, quark and this type of freedom, they are free in the small distance, but when distance of separation is slightly large, they are not free. This type of freedom is known as asymptotic freedom. So quarks are enjoyed asymptotic freedom on property. And okay, so whatever we learn. So this is the classification of matter. If we break a matter, we found matter actually made from two kind of particles, hadrons and leptons. And this hadron can be of two categories, baryons and mesons. And baryons contains 3 quarks and meson contains 1 quark and 1 antiquark. Quarks and leptons are the fundamental particles, and we have 6 types of quarks we already discussed: up, down, transient, top, bottom, and we have 6 types of also leptons: electron, muon, tau, electronic neutrino, muonic neutrino, and taionic neutrino. These 6 are fundamental particles. Besides this, also mediating particles, which are mediator of force, they are also fundamental particles. We cannot break them. They are the photon, gluon, double boson, Z boson, they all are fundamental particles. Besides them, our Higgs boson, which also is a fundamental particle, which is not comes under here because it is gives you mass. So these are the, if you want to construct particle by cooking, if you try to form different type of particles, then your ingredient will be leptons, quarks, and the spices will be these mediating particles, gluon, photon, W, Z, boson. By adding them, you can form any kind of particle. These are the fundamental particles, leptons, quarks, and mediating particles, which is commonly known as gauge bosons, are the fundamental particles of nature. Then this fundamental particle size is very small, so as I told, we cannot apply classical mechanics to study them. So quantum mechanics is needed to study them. Again, this particle, since the particle is very small, they move with high velocity. So for high velocity, you know, special theory of relativity can predict the motion of high velocity particles. So for studying elementary particles, we need a theory where both quantum mechanics and special theory of relativity must be satisfied. And that theory was first given by Dirac, and who attempt to combine the quantum mechanics with relative energy for studying this elementary particle. And you know, energy formula for in special theory of relativity is E square is equal to P square C square plus M square C to the power 4. So Dirac tried to solve this and get the energy. And if it is E square, if you take it, what is E? plus minus this square root of this, and so Dirac has plus E plus is equal to plus of square root p square c square plus m square c4, and E minus is minus of p square c square plus m square c4. But this equation of two roots, so one is for positive energy and another is for negative energy. So if you add special theory of relativity to quantum mechanics, negative energy particle can be possible. It has predicted, and so and he assumed that every particle must have a negative particle, or which is known as antiparticle, whose has same mass, lifetime, but charge is opposite. So for neutral particle, there are some of neutral particles their own antiparticle, or other have their other antiparticles depending on the quantum number. But charge for all charge particle has one antiparticle whose charge is opposite. Dirac predicted this by observing application of special theory related to quantum mechanics. Unfortunately, in 1932, T. Anderson observed the anti-electron, antiparticle of the electron, which is known as positron, validating this theory. So now antiparticle have the same mass and lifetime as the particle, but opposite quantum number like charge, lepton number, baryon number, third component isotope, other quantum numbers are opposite. So while all leptons have antiparticle partners with all quantum number remote but with the same masses. So you can write anti-quark by putting a bar over them. Anti-quark, anti-d quark, anti-s quark, anti-c quark, anti-b quark, anti-t quark. Similarly for anti-leptons, for electron, anti-positron will be E plus. In the charge, mu plus, tau plus. For neutrino as chargeless, so you put a bar. Anti-neutrino, electron, anti-neutron, muonic anti-neutron, tauonic anti-neutrino. So anti-electron is known as positron. Anti-quark of anti-color means anti-color, anti-red, anti-blue, and anti-green and anti-blue. Okay. So when particle and antiparticle meet, they annihilate to give energy. With all quantum number become zero. So if you two particle and antiparticle annihilate E plus E minus, they go to energy photon. Okay. Then next thing is other quantum numbers which these elementary particles have. One is isospin. Like spin, since nuclear forces are invariant for proton and neutron, whatever force exists between proton and proton, that type of force, that amount of force exists proton and neutron. For that reason, for that proton and neutron are substate of one state. And which quantum number defines this is known as isospin. And proton and neutron comes under one isospin multiplet, whose third component is plus of it is proton, third component minus of it is neutron. And like spin, isospin multiplet contains 2i plus 1 number of particles. Is the quantum number assigned to the particle, particularly hadrons, and hadrons are because most of the hadrons have nearly same mass for different charge. So they form a group which is characterized by isospin. But all leptons and gas bosons are isospin 0. And isospin is a vector, it has three components like spin. And I see the third component, I see for I is equal to 1, I see maybe plus 1, 0, minus 1. It's all just like spin. Then another quantum number is strangeness, what we discussed, the particles which contain S quark, generally hadrons contain quark, hadrons containing S quark or anti-quark of S have new quantum number which is known as strangeness quantum number, and these particles are called strange particle. Anti-particle have opposite strangeness than particle. And these are some particles which have strangeness exist, and lambda and sigma have strangeness minus 1, K particle contains strangeness plus 1, cascade strangeness minus 2, omega minus 3. Strangeness is conserved both electromagnetic and strong interactions. So these are the mainly quantum numbers. Charge, baryon number and lepton number conserve strong interaction. And they are called universal quantum numbers. And the article number so these quantum numbers must be conserved for a interaction. If it is a weak interaction, so only lepton number, baryon number, charge is conserved. Baryon has baryon number +1, anti-baryon has baryon number -1, other has no baryon number. And lepton number we already discussed, which are +1, -1. Then charge is generally given. This is pi minus minus charge. Proton you know plus charge, delta 0 0 charge. So charge is generally given in interaction. Another contains isospin and strangeness, which contains strange quarks. There is a strangeness and a group of particles form same mass particles form a group which is characterized by isospin. And isospin has a third component also. You can see some particle what is the isospin number. Before that, we can first discuss about the quantum numbers of quarks, because these quantum numbers, if you add, you get the quantum numbers of hadrons, baryons and mesons. Quark has spin half particles, and quark U quark has charge +2/3, D quark has charge -1/3, and S quark has charge -1/3. From this you can get the any combinations of the quark from baryon. If so, for example, proton is charging +1. So since its charge is +1, how you add these three? If you add 2/3 +2/3 -1/3, then it will be 1. So it contains 2U 1D quark. But for neutron, charge is 0. So if you add 2/3 with -1/3 -1/3, then it will be 0. So UDD gives you neutron. Similarly, and the strangeness S quark of strangeness number -1. This thing quantum numbers are not required for us for the time being. And then also anti-quark. Anti-quark charge is opposite. So anti-U quark has charge -2/3. Anti-D quark has charge +1/3. Anti-S quark has +1/3. And strangeness of anti-S quark will be +1. This and so since 3 quarks make you baryon, each quark has baryon number 1/3. Similarly, baryon number of each anti-quark is -1/3. From this combination, these particles are formed. If you combine proton, it contains UUD, charge 1, and its baryon number 1, isospin half, carbon half, and parity positive. Okay. All this table you can construct. Sir, how much time I have? Sir?
Hello, sir.
Hello?
Sir.
Yes, sir.
Hello,
How
sir.
much time I have?
You continue, sir. Just up to 10 minutes left, sir.
Okay, sir. Thank you. Okay. So from this you can construct baryons and mesons. These are the meson construction. If you add them quark, you can find this type of particles. Okay, this is the quark combination. If you form a meson are formed from one quark and one anti-quark. So if you combine it, since quark have spin half and anti-quark have spin half, what we have seen here in the table, anti-quark have also spin half. Okay, so half will give you 0 or 1. This is the combination of quark anti-quark gives you meson. Similarly, 3 quark combination gives you baryon. For example, proton is a baryon, it contains UUD quark, and neutron is a baryon, it contains UDD quark. Meson contains UD bar quark. Pi meson, K meson contains U bar S quark. Okay. So how you represent this? And as you know, generally we represent all in terms of picture. So we try to represent these interactions in terms of picture, and particularly Feynman who tried this, and this picture which represent particle physics interactions or elementary particle interaction are known as Feynman diagrams. You can represent interaction through suppose this gives you interaction between proton and neutron. So this proton neutron interaction under nuclear force, and this occurs due to exchange of meson. Or you explain exchange of meson. Nuclear force is due to exchange of meson. Nuclear force means the force exists between proton and neutron. So it can be pictorially given like this. One neutron comes here, one proton and one neutron combined. So exchange of let's say it can represent two ways. One is if you time goes from left to right and up to down. Here time is given in this figure up to down. That means the particle initial particle is the up section the final particle in the down section. So one proton and one neutron they interact through these pions and they again gives you neutron and proton. Since if you will pi minus, so exchange of charge occurs at each point is known as vortex. So P interact with pi minus give you neutron and that neutron accepts this pi minus and gives proton. So in this way exchange occurs. So in the pi minus proton you see this interaction is between quarks. Proton contains UD quark and neutron contains UDD quark. And they interact and quark interact through gluons and by interacting gluons they can give you this neutron and proton. So, and since here the theory contains quantum mechanics, so we call it in terms of theories and quantum terms. Electrodynamics is known as quantum electrodynamics QED, the study of electronegatory force. Similarly, study of strong force. Strong force is mediated by gluon and it involves quarks. They have color. So due to color, we call them quantum chromodynamics. Chromo means color. Since color involved in this extent, we call this branch of physics is quantum chromodynamics, where interaction of quarks occurs. And this is whatever quark. So the fundamental particles are electrons, quarks, and the mediating particles are gas bosons. And Higgs boson which gives mass, and the fundamental interaction are for strong, weak, electromagnetic, and gravitational interaction. Now come to what can we say about mass? Why proton is heavier, electron is lighter, how it comes this, and this was explained by Peter Higgs in 70s, but he predicted that there exists a field when a particle moves through that field, depending on its interaction time, it has a mass. In terms of a particle, he told that this field has a particle which is known as Higgs boson. It depending on time of interaction with other particles, it gives mass to that particle. And since it gives mass to all, it is popularly known as God particle, and it was discovered in 2012 in CERN, and whose mass is nearly 125 giga electron volt. So Higgs particle, which is also a fundamental particle, because you cannot break it, it gives you mass to other particles. So now what is the present aim of all this particle physics? Actually, present aim is to find a point where all forces are combined, which is known as unification. Because our physics becomes simpler with time when we use unification. As electric field and magnetic field are unified, gives you electromagnetic thing. So electromagnetic theory through Maxwell's equation then becomes simpler electromagnetic theory. And from one theory you get both in limiting case get electric field and magnetic field behavior. Similarly, space and time are unified, give a special theory of relativity. We consider both space and time. So people try to unify all four forces: strong, weak, electromagnetic, and gravitation. And first, they are successful in combining weak with electromagnetic, and that theory is known as electro-weak theory. Electro-weak theory. Then people try to combine with strong interaction, which is known as grand unification theory, and can combine all three interactions. And in unification theory, we are fortunate one of our Odia people plays a main role, Professor Jogesh Chandrapati, who is from Baripada, and he got the Dirac medal, only one Odia to got the prestigious Dirac medal in the second prestigious fight after Nobel Prize, and Professor Jogesh Chandrapati, whose contribution is towards this unification. How all four forces are combined, and till today we are able to combine three forces: strong, electromagnetic, and weak, which is the energy is very high when length scale is very small, order 10 to the power 16 GeV, then these three forces will combine, which is known as grand unification theory. But still we have a challenge how to combine these three with gravitation, which is known as theory of everything. How four forces are combined? Actually, this combination will occur at the Planck scale according to theory, 10 to the power 19 GeV. Not till yet we are not able to achieve that much energy, only achieving tera electron volt energy. So also there is not successful theory which can combine these four. For that different theories are put forth, and one of them is string theory, which is demanding that it can combine all four forces if we assume that particles are made from strings. So there's a quark and the electron structure, particle structure is not the fundamental one, rather they contain strings. Other type of demand is supersymmetry, particles exist using symmetry property. Each fermion has a partner, and each boson has a fermionic partner. This type of theory to explain the theory of everything, where four forces are combined. But still, it is a challenge, and we will try to solve it. So, finally, this is the picture of how electromagnetic and weak combined scale, then a strong and electroweak combined. Then our aim is to combine this grand unification theory to gravity, which is theory of everything. Till late, we are experimentally proved it, the grand unification theory, but we are unable to prove this theory of everything. May in future some days it may be proved when we go to high energy scale, or we are able to produce that much energy of 10 to 19 GeV. Or this may be wrong, you get another theory. So it is a challenge for particle physics how to give a successful theory which can combine all four forces, and also for observation how we see in our laboratory, mainly high energy lab like Large Hadron Collider at CERN, where the four forces combine. Okay, and thank you. Sir. Hello. Any questions? Yes, sir. Hello.
Yes, sir. Yes, sir.
Hello.
Yes, sir.
Hello.
Yes, sir.
Hello. Thank you, sir, for such a nice presentation. Sir's delivery was so good and informative. A complete description was given on the elementary particles in a very simple and picturization method, which makes the things to understand better. Further, a detailed knowledge was given about the quantum numbers, quarks, antiquarks, Feynman diagrams were explained by the totally diagrammatic method. So, thank you, sir, for such a nice presentation.
Thank you, sir. Thank you for your nice presentation. Now the floor is open for discussion. Some questions are there in the chat box. So I would like to request Professor Snigdha ma'am to coordinate the question answer session. Please, ma'am.
Okay, sir. So the first question our participant called Debasis Sahu. His question is, what makes the short-range forces to stop acting beyond the certain distances?
Because yes, sir. What is you can say nuclear forces are strong and weak forces short range. Actual this the mediating particle of weak force is much heavy, or if you compare the five as mediator, it has also mass is heavy. For the one reason is the range is mostly proportional to mass of the mediator. And due to that, you can say weak and strong interactions are mediated by heavy particles, so that the range is very small. And
Okay, sir. The next question. The next question from a participant named Chandan Singh. He wants to know what is the minimum distance between the two nucleus to interact with each other.
nucleus.
Yes, sir, nucleus. What is
Nucleus,
the
two nucleus.
yeah, sir, two nucleus.
Nucleus interaction means you say nucleus in the positive charge. So if you two nucleus, another nucleus has a positive charge. The electromagnetic interaction exists between them. Whatever with the that force is varies with R. If R is closer, then interaction will be more. Q1, Q2 by R square. That's one nucleus. Because when you come to nucleus, there is no other force.
Okay,
Okay,
sir.
nucleus size, and you got proton, then it will be strong interaction, and there is I will not about 50 meter. If parasitic is 1 meter, than that.
Okay,
But
sir.
if you call nucleus, then it is charged particle. We have electromagnetic interaction.
Okay, sir. The next question from a student called Debasi sir. Does any particle and antiparticle have equal spin and stability?
Speed is same, particle antiparticle is same speed and same stability. They stay for same time. Like lifetime is and mass speed all are same for particle and antiparticle. They can decay in same time. So you can say them stability.
Okay, sir. The next
About time
question.
electron exist, that means proton.
Okay, sir.
Hello.
The next. Hello, sir. Hello. Okay.
Yes,
The
sir.
next.
Audible.
Yes. The next question is why the topness of a top quark is -1, but bottomness of a bottom quark is +1. Again, why there is no upness or downness quantum state or number? This question is asked by his participant.
Terms of property isospin. They have isostar other quantum, but UV actually gives you general particles. Top, bottom, cells, they give particles. Because when S quark present, it has a special property strangeness. These particles will decay in weak interaction, form in strong interaction. They are not occurring in case of UD quark. UD quark is a normal quark which are characterized by isospin. Other particles have no isospin. They are isospin doublet. Similarly, like strange quark top bottom, when they are introduced, they have a quantum number. And as depending on of the with an up down charge strength top bottom, the upper layer of UCT, they have positive, and in the lower layer DSB. So SB are negative quantum number, T and C has positive quantum number. That's positive sign from but, if you want the property like S wave, this is a type of quark.
Okay, sir. One more question. Hello. Yes, sir. One more question is about string theory. They are asking, one participant asked about the string theory.
Yes.
Is it
In string
related
theory,
to? Yes, sir.
yes.
Okay.
Is it related to?
No. I am asking, is it related to the subject matter today?
Yes. String theory, actually in string theory, the people demanding that the particles are made from string. This particle means it has a structure, point-like structure. We are assuming elementary particle, it has a point-like structure. They are telling that the elementary things are not point-like, they are like string, rope, the ODA type, shape. They are not point-like. They have so when they and strings means they carry energy, and the mode of vibration, you can say mode of, like in strings, guitar, if one mode gives one sound, similarly one mode of vibration gives you one particle, another mode gives you another particle. That is the string theory.
Okay, sir.
Hello.
Thank you for okay, sir. Thank you for all the questions. Further, we don't have any more questions. Thank you so much.
Okay, thank you.
If any participants ask to any questions can unmute themselves and ask. If any question from any other participants, please unmute yourself and ask, please. I think there is no questions left. So it's a time to propose a vote of thanks to our honorable speaker and our respected participants for giving us time, their valuable time, and listening to us patiently. I would like to request Professor Gajendra Hansda sir, please propose a vote of thanks. Please, sir.
Thank you,
Thank you,
Professor.
Professor.
A very
Very
good
good
afternoon
afternoon
to
to
everyone.
everyone.
I am
I am
Gajendra
Rajendra
Hansda,
Hasta,
lecturer in physics, Udala
Udala
College,
College,
Udala.
Udala.
Deemed
Deemed
it
it
a
as a
great
great
honor
honor
and
and
privilege to
privilege to
propose the
propose
vote
the
of
vote of
thanks
thanks
on
on
behalf
behalf
of the
of the
principal
principal
and
and
Department of
Department of
Physics
Physics
and the
and the
IQAC of
IQAC
the
of the
college.
college.
At the
At
very
the very
outset,
outset,
I
I
convey my
convey my
special
special
thanks
thanks
and
and
gratitude
gratitude
to our
to our
honorable principal,
honorable principal,
Professor
Professor
Gopal Chandra Behera
Behera
sir,
sir,
for
for
giving
giving
us
us
permission to
permission to
organize
organize
this
this
webinar
webinar
and
and
providing us
providing us
all
all
possible
possible
support
support
and
and
encouragement.
encouragement.
I
I
extend
extend
I
I
extend
extend
my
my
heartfelt
heartfelt
thanks to
thanks to
our
our
today's
today's
resource
resource
person
person
and
and
chief
chief
speaker,
speaker,
Honorable
Honorable
Dr.
Dr.
Vivekananda
Vivekananda
Nayak
Nayak
sir,
sir,
Assistant
Assistant
Professor
Professor,
PG
PG
Department
Department,
Applied
Applied
Physics and
Physics and
Ballistics,
Ballistics,
Fakirmohan
Fakirmohan
University
University,
Balasore,
Balesore,
for
for
enlightening us
enlightening
with
us
his
with his
vast
vast
knowledge and
knowledge and
experience on
experience
the
on the
topic
topic
fundamental
fundamental
constituents of
constituents of
matter.
matter.
Sir,
Sir,
indeed
indeed
this was
this
a
was a
very
very
useful
useful
and
and
impressive
impressive
session.
session.
Your
Your
talk
talk
gave us
gave us
deep
deep
insights
insights
into the
into the
topic.
topic.
Once
Once
again,
again,
I
I
thank you,
thank you,
sir,
sir,
for
for
giving us
giving us
time
time
from your
from your
busy
busy
schedule
schedule
and being
and
a
being
part
a
of
part
this
of this
occasion.
occasion.
I
I
express
express
my
my
deepest
deepest
sense of
sense of
appreciation
appreciation
to
to
HOD
HOD
Physics
Physics
and
and
convener of
convener
this
of this
session,
session,
Professor
Professor
Snigdha
Snigdha
Agarwala,
Agarwala,
Madam,
Madam,
for, for her
for her
active and
active and
sincere
sincere
steps to
steps to
organize
organize
such a
such a
webinar
webinar
in the
in the
department.
department.
I
I
also
also
thank
thank
Dr.
Dr.
Prafulla Kumar
Prafulla Kumar
Ponda
Ponda
sir,
sir,
Coordinator
Coordinator
IQAC,
IQAC,
and
and
Satya Bhatta sir,
Satyabhata sir,
Assistant
Assistant
Coordinator
Coordinator
IQAC
IQAC
for
for
their
their
help and
help and
all
all
possible
possible
efforts
efforts
to
to
organize
organize
this
this
webinar.
webinar.
The
The
Department of
Department of
Physics is
Physics is
also
also
thankful to
thankful to
all the
all the
participants,
participants,
dignitaries
dignitaries
for
for
accepting our
accepting our
invitation
invitation
and
and
extending their
extending their
support
support
and
and
patience
patience
throughout the
throughout the
session
session
and
and
making this
making this
webinar
webinar
a
a
successful one.
successful one.
Last but
Last but
not the
not the
least,
least,
I
I
appreciate and
appreciate and
thank all
thank
the
all the
teaching and
teaching and
non-teaching
non-teaching
staff
staff
member of
member
the
of the
college
college
for
for
their
their
direct
direct
or
or
indirect
indirect
support
support
and
and
cooperation for
cooperation for
this
this
event.
event.
Once
Once
again,
again,
I
I
thank
thank
everyone
everyone
present
present
here
here
and
and
making this
making this
webinar
webinar
a
a
great
great
successful.
successful.
Thank you
Thank
very
you
much.
very much.
Thank you, Rajendra sir. Thank you, Vivekananda sir, once again.
Thank you, sir.
Thanks to all the participants for giving us time and listening to our honorable resource person. Here is an announcement for the participants. There is no feedback link. All participants will receive their e-certificates from the registration link. So if anyone has not registered, please register yourself and your certificate will be within 1 or 2 days. You'll get your certificates within 1 or 2 days, no problem. So just register yourself and don't wait for feedback link. Please. Thank you. Let me stop this session here. Thank you.
Okay, thank you, sir.
Thank you, sir. Thank you.